Okay, welcome back. 10.3 now. We want to admit calculus into these parametric equations. We want to be able to find, derivatives of these things. And one thing to note is that there are cusps in this thing, right? So in Calc 1, you probably said if something has a cusp, like, for instance, the absolute value function, it wasn't differentiable right here. So we have the same kind of issue here. And in this context, we're going to say that this thing is not smooth right here. And it'll be because the derivative of the x function. So before, when I was talking about parametric, making parametric equations of lines, I said there's like an x slope and there's a y slope, right? It's that's what it's really coming down to, is if both are 0, then this thing is going to be non-smooth at that point. So say it's smooth so long as you have the continuity of the derivatives, and they're not simultaneously equal to 0 at that point. Okay? So in the cycloid, we should have some non-smoothness issue right here. And let's go ahead and take a look at the derivatives of these, of the x and the y function of the cycloid, and show that they're both equal to 0 at these particular points on the curve. Right? So here's our formula from before. Let me rewrite those in terms of x. This is now 10.3. Parametric equations in calculus. Okay. All right, so first we deal with smooth curves. So to be smooth again, f prime and g prime are continuous. Okay. And I should note that our formulas now, x will equal some function of t, and then y we're calling the g function of t. Okay. So the derivative, the x slope and the y slope, if you want to think of it in that way, are continuous at the points. And then secondly, f prime does not equal 0 simultaneous at the same time when g prime equals 0. Okay, so you don't want them both equaling 0 at the same time. So maybe I should say f prime and g prime are not both 0. That makes me feel better. Okay, so the example then, again, we'll carry on with the cycloid because we kind of know where it's not going to be smooth. And I'll put the formula, I guess I'm going to put them in terms of t. So the x formula, which is our f of t, is going to be a times t minus a times sine t. So a times t minus a times sine t. And then our y formula is going to be a minus a cosine t. Okay, so you take the derivatives. X prime is going to be a minus a cosine t, and then y prime is going to be 0 minus a times negative sine t, so just positive a sine t. I'm going to set them both equal to 0. They're defined everywhere, so there's no issues there, but let's set them equal to 0. A minus a cosine t. Okay, so I'll have a cosine t equals a, and then cosine t equals 1. So I'm looking for where cosine is equal to 1. That will be when t is equal to 0 plus 2 pi n. And then over here, set this equal to 0. So 0 equals a sine t. So 0 equals sine t. And sine t will be 0 when t is equal to pi, well, just 0 plus pi n. Okay. So they're simultaneously equal to 0 at multiples of 2 pi n. Okay. So x prime equals y prime equals 0 when t equals 2 pi n. Okay, so what points are those? Let's find these 2 pi n points, and to find those, you just put these into these equations. Okay, so my x values will be a times 2 pi n minus a sine of 2 pi n. Of course, sine of any multiple of pi is 0, so the x-coordinate will be 2 pi, let's write 2 pi a times n. And then my y-coordinate, so now I'm plugging 2 pi n into this formula, so I'll have a minus a cosine of 2 pi n. So y will equal a minus a cosine of 2 pi n will always be equal to 1. So you'll just have a minus a, which is 0. Okay? So the cycloid is not smooth when we have the points 2 pi a n comma 0. And of course, if you look back at our curve, certainly when n is equal to 1, we get our first cusp happening. And it's not considered smooth right there. Okay, so there's that. Smoothness is an issue. Let's now look at the parametric form for the derivative. And basically what you're doing is just kind of looking at the x derivative and the y derivative, and then to get it into a rectangular form, you kind of can take its ratio. So, I don't know. Anyways, let's see. So section 2 then, the derivative. So we need smoothness to apply, and if our parametric equations, x equals f of t, and then y equals g of t. The derivative of y with respect to x will just be the derivative of the y component function with respect to t divided by the derivative of the x component function with respect to t. Okay. So we could do this for the cycloid, and its derivative will end up being the derivative of where the heck was that formula? So the y part was a minus a cosine t. Its derivative we found was a sine t, and then the derivative of x was a minus a cosine t. And the derivative of once you form this derivative, you should be able to kind of back engineer the, I don't know, let's look at number 3, okay? So number 3, we have the derivative of y with respect to x. We want to find this, okay? So find that thing. Our formula is x equals sine squared theta, and then y equals cosine squared theta. So our derivative, dy with respect to dx, is the derivative of this over the derivative of this. The derivative of this is 2 cosine theta times the derivative of cosine is negative sine theta, all over the derivative of this is 2 sine theta times cosine theta. This is then equal to negative 1. Okay, so what I'm kind of saying is that this slope makes sense. It may not seem like it makes sense, but it is the slope of this graph. It's constant, so it tells you that it's basically a line. It's a line with slope negative 1. And you can see that by kind of eliminating the parameter using our Pythagorean identity, sine squared theta plus cosine squared theta equals 1. Right? So sine squared is x, cosine squared is y, that equals 1. So y is negative x plus 1, and then of course the derivative of this is exactly the derivative that we got right here. The derivative is negative 1. Okay, so there's this alignment. It seems like they're kind of disconnected in the universe, but they're actually connected. Okay? The rectangular and the parametric derivatives. Okay, higher derivatives, you can't just, like you do with in the rectangular coordinate system, when you're differentiating with respect to x, you can't just keep taking the derivative over and over. You have to change things. So for the higher derivatives, then you have to follow a bit of a different formula. 1, 2, 3, higher derivative. The second derivative with respect to x is going to be the derivative with respect to x of the original derivative, right? And so how does that work? What you're doing is taking the derivative with respect to t of the first derivative that you found, and then dividing it by the derivative of the x formula with respect to t. Okay, so let's look at number, well, let's go back to the cycloid example again, right? So our formulas for the cycloid, we had x equals at minus sine t, and then y equals a minus a cosine t. Okay, so the first derivative, we already got it. You know, you can do the derivative separately here. So you have a minus cosine t, and then y prime is, well, 0 minus a times minus sine, so a sine t. And so the derivative with respect to x is going to be this over that. So a sine t, whoops, there should be an a right here, sorry. A sine t all over a minus a cosine t. We could simplify a little bit by factoring out that a. So we just get sine t all over 1 minus cosine t. Okay, and then the second derivative, what you're going to have to do is take the derivative of this thing and then put it all over the derivative of x with respect to t. Okay, so for this thing, I need a quotient rule. So low 1 minus cosine t times the derivative of the high, which is cosine t, minus high, which is sine t, times the derivative of the low, which is 0, and then negative sine t is just plain old sine t, and that's all over then 1 minus cosine t squared. Okay. So that was the derivative of the original derivative with respect to t. And then below, you have to put the derivative of x with respect to t. Okay, so the derivative of x with respect to t is right here. And I have a minus a cosine t. So I'm going to end up with a negative cosine squared minus sine squared, which is just 1 from these two elements. And then you have a cosine t. So it's going to be cosine t minus 1 all over 1 minus cosine t squared times the reciprocal of this thing, which I can write as 1 all over a times 1 minus cosine t. Okay, this is the negative of this guy, right? These guys are additive opposites. So you can remove this and put a negative 1 up here, and you end up with negative 1 all over a times 1 minus cosine of t squared. So the second derivative is less than 0. And what does that tell you? Well, that tells you it's concave down, right? It has that shape to it. And of course, we go back and look at this cycloid thingamajig, if I could frickin' find where I put it. Well, I can't, obviously. That would be too easy, but here it is. The cycloid is always concave down, right? So this just verifies that factoid. All right, great stuff. So what? Let's see what else we got. Higher derivatives. Some standard kind of problems in the homework, finding the equation of the tangent line to a point on the curve. It's number 17. We have our parametric equations. X is t squared minus 4. Y is t squared minus 2t. I want to find the slope of the equation of the tangent line at 0, 0. Find tangent line at 0, 0. Okay, so I need a slope. I already have a point, so just need a slope. So the derivative of y with respect to x. You know, the power of this, you could eliminate the parameter, but it doesn't look like it's going to be a lot of fun. So you can actually find the derivative and get a slope of the, get an equation for the tangent line without having to actually explicitly find what the equation is in terms of rectangular coordinates, right? So derivative of y is 2t minus 2. Derivative of x is just 2t. Right? So the slope, and sometimes they'll draw it like this. So they'll draw evaluate at t equals something. So in our particular case, we need to figure out what that t value is. So you can plug 0 in for x. 0 is t squared minus 4, and 0 in for y. So 0 is t squared minus 2t. Okay. So here, t squared is 4, so t, it'll happen at plus or minus 2. Over here, t minus 2, it'll happen at t equals 0 or t equals 2. The t value you need is the one where they're both simultaneously at 0, right? We need this coordinate to happen on the curve, not -2 something else. If you put -2 in there, it'll be 0, comma 8. 4 plus 4, 0, comma 8. So that's not 0, 0. You need the one where it's +2 and +2. If you use 0, this will be 0, but then this will be -4. Okay, so you need the t equals 2. Okay, so plug 2 into that formula. You get 4 minus 2, which is 2. All over 2 times 2 is 4. In other words, the slope for my curve, my line is 1/2. So then go to your y minus y1 formula equals m times x minus x1. And you get y minus 0 is 1/2 times x minus 0. In other words, y is 1/2 x. Great. We'll spend some time looking for horizontal tangents, just like you did in Calc 1. Horizontal tangents, of course, would allow you then to maximize the function. Those are where the critical numbers would occur. We're not only interested in horizontal tangents, but we can also now track down the vertical tangents, right? So before finding the vertical tangent line, that was, that was a matter of having to go back to the limit definition of the derivative and getting that thing to equal infinity. Those were places where you couldn't find the derivative in the case of the rectangular coordinate system. But here you have a method for that. So that's another, I guess, advantage of working in parametric equations. Okay, so let's look at that section 4, horizontal and vertical tangents. And what does that come down to? Well, for the horizontal tangents, the y prime will be 0 and x prime will be not 0, right? For the vertical tangent, then that's when sort of the bottom of dy over dx is 0 and then the top is not, right? So what you do is take the derivative of the x formula, set it equal to 0, find those places, take the derivative of the y formula, set those equal to 0, find those places, and then you can identify the horizontal and vertical tangents, so long as they're not both 0, and in those cases when they are both 0, that's where it's not smooth, right? Okay, so 33 then, let's take a look at this issue. We're dealing with some trig material. So find the horizontal and vertical tangents for the parametric equations. X equals 3 cosine theta, and then y equals 3 sine theta. This problem is especially nice because we know that this is just going to be a circle. If you eliminate the parameter using Pythagorean formulas, you'll note that cosine theta is x over 3, sine theta is y over 3, and therefore if you take cosine squared theta plus sine squared theta, equaling 1, you have x squared over 9 plus y squared over 9 equals 1. You have x squared plus y squared is 1 in the rectangular, is 9 in the rectangular coordinate system. And then 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. There's our circle. We should have horizontal tangents there, vertical tangents there. Okay, so we know the answer is what I'm getting at. Okay, well, but let's use this new sort of way. I'm going to take the derivative of the x function, so I get negative 3 sine theta, and then take the derivative of the y function, so I get 3 cosine theta, and then we're setting these guys equal to 0. Okay. I need where to find the theta values such that sine of theta then is equal to 0. So that will happen. You may want to have to think about your unit circle, right? So sine of theta is equal to 0 when theta is 0, pi, 2 pi, 3 pi, 4 pi. So it's at multiples of pi. So you could say n pi. Then for y prime, so 0 is 3 cosine theta. So I'm looking for where cosine theta is equal to 0. And that happens at pi over 2, 3 pi over 2, 5 pi over 2. So in this case, theta is going to equal pi over 2, and then you're adding in multiples of pi. Okay. So these guys will never simultaneously be 0, so we don't have to worry about the smooth issue. I just need to find where when x prime is 0, those will give you the vertical tangents. Okay, so for the vertical tangents, then that will happen when you have n pi. So placing n pi back into the original formula for x, I get x equals 3 cosine of n pi. Okay. So that would be plus or minus 3. And then the y coordinate will be 3 sine of n pi, which will always be 0. Okay, so our vertical tangents should happen at 3 comma 0 and then negative 3 comma 0. And if you look back on your graph, well, here's 3, 0, vertical tangent, negative 3, 0. Okay, it works. Let's go for the horizontal tangents then. And we're plugging this formula now into our original equations. So when y prime is 0, you'll get the horizontal tangents. So for the x coordinate, x equals 3 cosine of pi over 2 plus pi n. And of course, cosine of that is just 0. And then y equals 3 sine of pi over 2 plus pi n. So that would be things like pi over 2, which would be positive 1 times 3, negative 1 from the 3 pi over 2, so negative 1 times 3. So this is either plus or minus 3. Okay. And then, of course, our coordinates for the horizontal tangents will be at 0, 3, and then 0, negative 3, which is what we predict, right, from our graph. 0, 3 is here, horizontal tan. 0, negative 3 is here, horizontal tan. Okay, the last part then is an arc length formula for these parametric curves. You'll have several arc length formulas once you get into Calc 3. So we want to obviously introduce this guy, arc length formula. And you can kind of get it if you remember the arc length formula in the rectangular coordinate system, which would have been the square root of 1 plus f prime of x squared dx. Okay. So using the definition for the derivative of the parametric equations, we know dy over dx, which is this thing, that's equal to dy with respect to dt all over dx with respect to dt. So I can replace that. I get the integral of the square root of 1 plus what do we get? Dy over dt over dx over dt squared, dx. Then I'm going to factor out 1 over dx over dt. Okay, so this will equal the integral of the square root of dx over dt squared plus dy all over dt squared times this thing I factored out, 1 all over dx over dt squared, and then I have dx. Then you can use the square root property to chop this part of it off, and you have the integral of the square root of, let's rewrite dx over dt as just x prime. Okay? So x prime squared plus y prime squared, and then the square root of this is 1 all over, I guess I'm just going to leave that as dx over dt, and then times dx. And then you could take the reciprocal of dx over dt as dt over dx, and you're just left with the parametric form that we're after. Okay. The problems in the book are pretty simple. They'll give you the information you need. So this is like, I don't know what problem this is. I cannot read my own writing. So we'll just call it an example. They give you the formula, your parametric equation, 6t squared, y equals 2t cubed, and they're going from 1 to 4. Okay. So I'll take derivatives. X prime is 12t, y prime is 6t squared. I plop those into my formula. So the arc length S is going from 1 to 4 of the square root of 144t squared plus 36t to the 4th dt. I can factor out a 36t squared, and then the square root of 36t squared is going to be 6t. So I have left over 4 plus t squared dt. And then you can do a u sub for the guts here. So u for 4 plus t squared. Du is 2t dt, and then dt is du over 2t. Okay. So this will equal the integral of 6t times u to the 1/2 times du all over 2t, which will equal 6 divided by 2 is 3. Integral, the t's divide out, I get u to the 1/2 du. Then I have 3u to the 3/2 times 2/3. Evaluate that eventually, so you'll end up with 2 times 4 plus t squared to the 3/2. Evaluated from 1 to 4. So that would be 2 times 16 plus 4 is 20 to the 3/2 minus 5 to the 3/2, whatever the heck that is. And I got an approximation, 156.52. So pretty simple stuff. But like I said, Calc 3, you're going to get multiple formulas for arc length, and use them depending on the scenario that you're in. Okay? All right, thanks for watching. Bye-bye.